All right. Well, thing has gone red. Well, that must mean we're alive. Hey guys, what's going on? Memes here. So, yes, as we're getting back into a little bit of a groove of things, I noticed that PBS Space Time had dropped a new video, and they touch upon some very interesting things. So, what we're gonna do is the link is in the doobly doo. If this is something that interests you, feel free to go check it out. Do as you will. Nobody's required to watch this thing here. But my big thing is one of the reasons I'm talking about is they have an ongoing thing, and they like to have a little bit of an arc, so to speak, talking about different topics. So they bring back some different uh, topics and questions, let's say, about hierarchy problems and all that jazz. And it's like, is there a simple proof for the multiverse? So rather than bloviating, let's let's jump right into it. Ah, the internet memes. Ah, yes, good old Philip DeFranco. Welcome, David. Good to see you, my friends. As folks now are temporarily rolling in, joining us in the future. Uh, and basically, if you're going to do a response video, the one thing that I've learned is it takes forever to get through it, especially if you're trying to do it copyright free. Now, this is PBS Space Time, so I'm assuming there shouldn't be any issues because this is brought to us by viewers like you. Um, we'll see. So let's just bring this up, share it with the class. All right. Boom, boom. Yeah. So as we can see, is there a simple proof for a vast multiverse? Let's get
Thank
into
you
it.
to AnyDesk for supporting PBS. In 1987, Steven Weinberg wrote a cute little paper entitled Anthropic Bound on the Cosmological Constant. I say cute and little because this work feels minor in comparison to, say, electroweak unification theory that won him the Nobel Prize. Weinberg
Oh, I mean, is that all? I mean, Steven Weinberg. I mean, he basically helped putting together the standard model as we know it, at least to my knowledge. Yes, yes, the Electro Weak Center and everything. Yes, yes, a slightly minor paper that may exist. Why explain why we're here versus that? So, yes, let's continue.
was foundational in establishing the Standard Model of particle physics and represented an enormous leap in our understanding of how this universe works. But his little 1987 paper, although more obscure, may tell us something about how the multiverse works and can even be thought of as evidence for the existence of an enormous number of other universes.
Ooh. All right. They're jumping into it and they're selling a little Sir Roger Penrose merch there. Uh, listen, hey, if you want to get a Penrose diagram t-shirt, Space Time are your folks, I guess. Okay. So let's jump back. Let's continue and see what we got.
We asked whether it's bad science to hypothesize a multiverse. We concluded that it very much depends on where the particular multiverse comes from. But in general, we concluded that if a theory predicts a multiverse but isn't itself concocted with the intention of producing a multiverse, then we can't just necessarily dismiss the theory on aesthetic grounds. For example,
Okay, so I think some of the key words here are Everett interpretation, because I believe Professor Sean Carroll happens to be a big fan of the Everett interpretation. We're measuring something real. It's like the wave function doesn't actually collapse what happened. Oh, we got all these different multiverses and everything like that out there, and it's branching around and doing all that stuff. And maybe that is the case. Maybe there are literally an infinite, I don't know if whether they're countable or not, number of universes. Okay, see, the thing that bothers me about this is the old definition, or at least the definition of universe is all encompassing, all that jazz, and literally a bag of chips. Yes, I just happen to have a bag of chips sitting there. Um, okay, maybe that is the case. Maybe that is the case. That doesn't always seem the most efficient thing, but I could imagine something like that. Or you take the other version of that is, well, if there could be so many configurations, if you have infinity, that's a long time. and you could potentially get different configurations. Now, I don't know whether that's the case or not. Again, I wasn't there at the beginning. I'm just a dude in a meat suit that appears to be here now. At least that's what I think. Okay, we continue.
example for a violation of Occam's razor. But that doesn't help with the testability of the hypothesis. If we can't ever travel
Oh,
to or receive a signal from another universe, how do we know they exist?
oh, exactly.
Falsifiability is another hallmark of good scientific hypotheses. And so the multiverse is in danger on that front. But actually, there are ways to test the multiverse hypothesis without
Ooh.
ever leaving our universe.
Oh yeah, if I hold down, it goes double time. We could probably just do that for the other parts that we could just kind of skip through there. So now, what I have heard from Sean Carroll is people will complain, "Oh, there's no way you can falsify the multiverse, this and that," and then I'll hear Sean Carroll say, "It's like, all right, yeah, you can." I believe something inflation. I think it was. Does it have to do with the B modes? Is that what it is? I feel like I should have asked Professor Keating this the other day when I had him on a call. I'm just curious about the Simon's telescope, or the Simon's Observatory, and apparently there's also the Simon's Ray as well. But at least I have on the down low that hypothetically, if there was a preferred direction, so to speak, to universe, uh, that is something that is within the Simon's Observatory's ability to actually detect. So that should be interesting. I know he had posted some a little bit of a map with some CMB with some, I don't know, some lines that I don't know, got the old noggin a jogging. I don't know, like they didn't seem to be arrows, they didn't seem to be vectors, just seemed to be some lines around there. So all right, let's get back to the Matto Dowd.
Our universe has several properties that seem particularly well suited or finely tuned for the formation of life. If the binding energy of helium was a bit lower or a bit higher, then we'd have either only hydrogen or no hydrogen,
Huh?
respectively. If a very specific nuclear energy level of the carbon 12 nucleus was a bit different, stars wouldn't produce an abundant supply of this
Oh,
life critical element.
so okay. So I think this goes into, you'll hear the term finely tuned. What the heck does that mean? It's like, well, some folks will often go into the realm of, well, it's an anthropocentric argument. We're arguing because we are here to argue about it. Perhaps universe, or whatever verse we may be in, is actually designed to have observers like us. I mean, that seems kind of out there. That seems like a lot of the ancient tales from like scripture and stuff. And again, I don't know what the answer is. I can't get something from nothing. That's my big thing. Um, so very often here, let's go forward just a little bit so we get to the
Another
last part.
example of an apparent fine tuning that we've talked about recently is the small mass of the Higgs boson, which, for reasons
Well, we're gonna pause right here, and basically a lot of this stuff is. I think they've had a couple of videos, and there's a couple other creators as well. They'll say it's like, oh, speed of light isn't fundamental, blah blah blah, because of units, yada yada. But they'll say like something like the fine structure constant is actually fundamental, and depending on that, if that were to change a little bit here, a little bit there, like I don't know, like less than one tenth, I don't know, we know it's like nine significant digits. We argue about the 10th plus significant digit there. Um, yeah, yeah, but basically, if it was half as much or a quarter as much, yeah, everything would go wonky because all those other things are related. And then you get the fine structure constant because that's basically, uh, I have another thing. It's basically the 1 over 137 thing. I go through some of the calculations later. But basically, it's the ratio of the electron, excuse me, the elementary charge of either an electron or a proton divided by the Planck charge, and you square the whole thing. If you don't square it, you get the amplitude, or That was kind of what Professor Feynman referred to as the fine structure constant, which is basically what most people consider the amplitude nowadays. It's interesting. It's interesting. Before, universe was everything. Now it's obviously got to be a multiverse, and we're only the changing of language over the years, my friends. Let's see what we got. We got some folks here. Uh, Jeremiah is saying a universe within a universe. Well, depending on one's interpretation, hey, that might that might make a lot. It's David's commenting that they hooked up a timing light to the universe. Those Vorlons are I forget what the in the three body problem, at least the Netflix series, I forget what the that that group of beings that was supposed to be 400 light years away and traveling at 1% the speed of light using their cell phones to mess with all the jazz and everything. Like, I actually enjoyed it. I'd like to see a season two. And actually, I got recommended. I'd started watching the Chinese version at one point. Um, and it did actually seem more sciencey, which was kind of cool. Um, it's only in subtitles, so some of the folks I was with before didn't feel like reading subtitles. So I still need to watch that. I did watch start of Alien Earth. I enjoyed it. Some folks weren't fans. That's fine. Okay, we're talking about the Holy Spirit. It's listen, I'm not a theologian or anything. It's just my personal opinion. My personal opinion. Again, I don't have any evidence for this. Is The more I learn about science, the more I personally believe in God. That was not something I was expecting just because I'm like, this is too dang beautiful. It's again just personal personal feeling. Uh, everybody to their own. Oh, the Troilocarans or something. Yeah. Let's see. It was Orion. Oh, okay. That sounds right. Hold on. Three body. Well, I mean, I really don't care that much, but aliens. Yep. The Trisolaran, the alien species, or at least when I put three body problem aliens into Google, and then it comes up with alien species fandom. That, yep, that seems about correct. Yep, that one. Okay. So again, I have no idea. But these little things, if you were to change them a bit, it would affect a lot of things. Let's go back here because now we're talking about the small mass of the
Since
Higgs.
we discussed and will review, seems oddly teensy. Related to this is the smallness of the strength of gravity compared to the other forces. If
Ooh.
either the Higgs mass or the strength of gravity were larger, matter would scrunch up into blobs too dense to form interesting structures, or just into black holes.
Oh wow. Well, sound like really big problems. I mean, if somebody actually find a way to explain either of those things, that sounds pretty important to me. But again, I'm just a dude on the internet, so what do I know? Continue, Matt.
The separation in scale between the Higgs mass and the Planck scale and the weakness of gravity and the other forces are both examples of the hierarchy problem. Another example is
Oh, that's one of our key words. Hierarchy problem. It means I need a drink again. And or I need to finish my caffeine before it gets too late. Otherwise, I will never go to sleep. Okay, the hierarchy problem. This has been discussed on previous episodes. Only we could find potential solutions to these problems that many smart people say are very important.
the apparently very tiny value of the cosmological constant.
Oh,
The cosmological constant is a number that appears in the Einstein field equations of general relativity.
it's this thingy here. It's that lambda thingy. It's the capital A without the little cross through it there. Okay. And you got 8 pi g. This is just the Planck force. It's 8 pi divided by the Planck force because C4 over the big G thingy over here just ends up, it just gives you the dimensions of force in Planck units. So that's just what that is. That was first founded out to me by Dr. Salvatore Pius and Rick the Wicked, as well as It's basically use similar notation. So I'm like, all right, this it's just an easier way for me to think about it. Rather than, oh, you got this, you got this. This just the maximum of force. Cool.
activity, which, if positive, causes accelerating expansion of the universe. The expansion of the universe is indeed accelerating, and so the cosmological constant is indeed positive. We call this effect dark energy, and while we don't know what it really is, the most routine explanation is that empty space has a constant energy density. This is sort of maybe expected due to the high
Okay, so again, it's the dark energy, that stuff which we don't know what it is. It's some mystery there. It makes up, as far as we understand, about 70% of our realm. So about 70% of the universe is I don't know, some stuff out there that seems to be driving things apart and everything, and we don't know. And even the term is weird when you see, because when you look at it's described as dark energy, but when you're talking about the cosmological constant, it's expressed in inverse meters squared. So basically, you have area and with a one over it. Why? Mhm. So it's why I don't know. Maybe there's something interesting going on. Is it possible? Perhaps we could get a clue. We continue with our little review.
Heisenberg uncertainty principle, even a perfect vacuum can't be considered to have exactly zero energy. And positive energy density of the vacuum has the effect of causing accelerating expansion. We've now seen that our universe is accelerating, which means that we know that something like this vacuum energy exists, and we know how strong it is. In the
So, okay. The interesting thing that if dark energy is a thing, and we don't know precisely what it is, what what might be going on? Why might this be the case? And you'll hear all these different things. They go through a whole bunch of different calculations and everything. And as I'm talking right now, I totally just had a brain fart and forgot what I was supposed to be talking about. So we'll just go back to Matt and just continue as hopefully a little bit more caffeine will help
the
me.
modern universe, there's more of this dark energy than all of the other forms of energy combined, by a factor of nearly 2.5. That sounds like a lot, but it corresponds to a minuscule energy density of empty space. The only reason dark energy is so dominant
Oh, okay. It's all of the things that annoy me from what I remember learning in chemistry and some different physics class and stuff. The two things that really bothered me. Okay. Number one, an electron is a point particle, but it exists in all these places at the same time. I'm like, that doesn't really make sense to me. You're saying, well, it's kind of like a charge gradient that's whirling around, doing all these crazy things. When it's in an atom, it's making all these different crazy orbital shapes and everything like that. I'm like, listen, I've watched Naruto. I've seen him charge up a Rasengan. It's basically just a little crazy spinning around angular momentum, like hypersphere type thing with an energy gradient in it. I'm like, oh, I've watched anime. I can at least conceptualize that. Just be like, all right, you get some charge gradients doing weird things that we don't quite understand. That's at least like you're at least explaining in the way that at least we know it, rather than saying, well, we consider this a point particle. Why? Because there are reasons? I don't know. Uh, I don't know if you're just trying to divide it by like I don't know, like point, so like zero dimensional. So if you're trying to divide by zero, nothing crazy has ever happened when we divide by zero. Uh, oh, and the second part is the vacuum. I feel like, and I can say this because I'm part Irish. Um, is it kind of like no true Irishman? It's like there's no true vacuum. We use the word vacuum, but we're saying, well, even when we remove all the standard, like particles, photons, all the stuff that we'd actually account for, there does seem to be some base energy there. So it's not a true vacuum. aka no true vacuum. Uh, so that's why I often like to say it was I think when we were at the Wolf in summer school, I think at a moment at one point I was like we should just say the speed of light in the medium. Just don't specify, just speed of light in the medium because that's what we're talking about. Because if you're talking about the speed of light in water is a bit different than it is if it's in the vacuum. That's not a true vacuum, aka it's the speed of light that's in a medium. I think it might also annoy some people, but as long as you're factually correct, sometimes a little bit of a change in perspective might be useful. I like the whole minimal inputs for maximum effect. I think that's the power of my. Oh, uncertainty is me, Poindexter. That's the thing. Yeah, it ain't just a principle. It's basically every day of my life. Jeez. Don't that beat all? All right. We continue.
is that after nearly 14 billion years of expansion, there's just so much empty space that the dark energy adds up. Okay, so our universe seems to have this tiny energy density of the vacuum. If we go ahead and use admittedly naive methods to calculate what the energy of the vacuum should be based
Okay, number one. Thank you, Matt O'Dowd, for finally saying that. Because this is something like whatever you think of Dr. Hassenfelder. She has been stressing that it's like, whose calculations there was 120 order of magnitude difference and stuff. It's like, who is that thing? At least he said if we do the naive calculation, i.e., if you just throw in Planck units and you just calculate for pressure, you get the Planck pressure, which is like 10 to the 113 pascals. Which why would anybody believe that? Because like that's literally the maximum pressure. If you have that pressure, you're essentially going to, as far as we know, collapse into what we call a black hole. Personally, I'm more of a fan of the term mass hole. One, I think it's more accurate. Two, I'm born and raised in Massachusetts, so I have been a long term, so to speak, mass hole, quote unquote. Uh, because, hold on, he's going to get to it, and I'll bring it up.
on the expected activity in the known quantum fields, we get a number that's quite a bit larger than we observe, 120 orders of magnitude larger. While this
Okay. So, number one, what, why is this the case? Hey, Jedi, good to see you, my friend. Oh, well, you're from Massachusetts and you have the requisite mentality. By all means, you could be a masshole as well. Oh, are you still on mass, or I feel like we may have gone through this. I always get so confused. There are some people I feel bad because even was it when I went up to oh God Seattle, there were at least two people I knew that I actually talked with on a uh, okay regular basis that I didn't even hit up because one I forgot. The other person for some reason I thought he lived in like Tennessee. Or I don't know. I must be just stereotyping. I'm just a terrible person. Ah, Florida now. Okay. All right. I was gonna say, hey, we could go catch up, grab a drink or something. I caught up with Thomas Sully and one of their friends, Brian, over the weekend at Fan Expo, and yeah, no, I mean that was a good time. I may or may not have ended up blowing a bunch of money on the three Egyptian gods because well, they had some big poster printouts and everything, and I'm like. Dang, you have to offer the three and like buy two get one free. So I'm like, at first I'm like, well, I kind of want Rob. I'm like, oh, I also like Obelisk, and I'm like, oh, if I can collect the dang set, take my money. These things happen. Oh, man. Okay. That's gonna be in a week. If you're going through Massachusetts, and you're up like the I-95 or I-93 corridor. Actually, Maine will probably be hitting up the I-95 corridor. Uh, Let me know. I'm in northern Massachusetts. I'm like just south of New Hampshire. So if on that day you're going through, let me know. Maybe we'll stop, grab a bite of something. So yeah, that would be cool. Uh, Hey, that's how I learned. When I was up in Canada, I went out with Mads and her daughter, and she educated me on poutine, and I had my first poutine up there. So yeah, cool beans, man. It's Leominster. Oh, that's Johnny Appleseed City, I think, or at least is it? It's either Leominster or Worcester. Yes, yeah, yeah. Worcester is how it's typically written, but we call it since we're Massals, we call it Worcester. Like a rooster, but with a woo, because we can. Back to dark energy. Okay, where the heck does this 120 order of magnitude thing that's not actually what they said, where the heck does it come from? Okay, number one, the 120 order of magnitude. Okay, let's just do this real quick. Screen to a window. All right. Boom, boom. Okay. So we have this 120 thingy right here. 120. All right, keep that in mind. First, let's figure out what the heck we're supposed to be referencing to. The dark energy for the observed universe. Okay. So we're looking for the vacuum energy density. So universe, vacuum energy density. Okay. Gives you this number here. Okay. Don't worry about this. This is just this is an energy density. Okay. So it's energy joules divided by meter. All you need to know is it's basically at the magnitude 10 to the minus 10. All right. So within our realm of units, whatever you think about it, within our coherent system of units, it's at minus 10 magnitude. Okay. So if we go from that, and we go, oh, let me just make a new one. Boom. And we just put in the blank pressure. Under pressure. Gives you all this jazz here. Okay. So let me just make sure. Okay. So this is considered pressure, but if we look at the units, did I get this right or wrong? Okay. These have the same dimensional units. This is a mass of E equals mc squared. So if hold on, let me just do the quick little thing here. All right. I removed myself. Let's do the real quick thing. All you literally need to know is just the generic Einstein E equals mc squared thingy. Okay. Why? Because that's all you really need to do. You go through here. All right. So E equals mc squared. Blah blah blah. Making energy. Boom. Equals mc squared. Boom. Okay, that's people have heard about that. Maybe they don't even necessarily know what it means. Hey, E equals mc squared. Oh, it's something something Einstein. Okay. So energy. Let's break this up. So if you got mass, so you got mass. What is c? C is the maximum of speed. What's speed? You go a distance, and then you have your unit of time. So if you're going 60 miles an hour, 100 kilometers per hour, or something like that, that's the distance you will travel in that given period of time. Okay. So what is that? It's your length or your distance traveled. So you got a length, you got a length. It's divided by a time. With a little protective brackets on, you square the whole dang thing. Uh, that's literally what it is. So when we go back over here, basically that's why when you see these units here, uh, pressure just means that you're taking this energy and you're dividing it by a volume. So what does that mean? Because if you square this whole dang thing, that's just length squared. So if you divide it by volume, which volume is, you got one dimension. You got two dimensions. You got three dimensions. Bada boom, bada bing. You got your cube there. You're just putting that energy into a volume, aka you're going to divide it. That's length cubed. So you just nix out those two dimensions of length, and then there'll be one dimensional length in the denominator. So it's, listen, it took me a while to figure this out, but it literally, I'm just counting. It's literally like counting blocks or dimensional ingredients. That's one of the reasons why, like, when Thad taught me using Planck units, the only reason I got to like figure it out because they're essential ones within the system. So when we go back over to our friend over here, all we got is joules is just that mass, and then c squared. Okay. So if we divide it by meters, cubic meters, we go from length of +2 just down to -1. Everything else stays the same. Okay. So this is the vacuum energy density of the universe to the best of our knowledge, and there's maybe some caveats there for some different stuff. There might be other reasons. So again, full disclosure, but this is what we consider to be the minimum energy. There seems to be some energy around there, and it's actually, yeah. Um, so basically, it's the universe vacuum energy density. So again, magnitude -10. Okay, so we got a -10 magnitude. Again, we got these dimensions, mass, and then the negative thingies here just mean it's in the denominator. That's all it is. If it's a positive thing, it just goes up top. If it's negative, it just goes down below. So multiplication, division. Again, that's the only way I'm able to do this stuff because I don't need to run some triple integral over all these potential things and stuff. Uh, but over here, within Planck units, the units of energy density, or its interpretation is pressure, but mass, length -1, length -1, time -2, time -2. These are dimensionally equivalent. So the Planck pressure could be considered the Planck energy density. Okay. Note, this is at exponential power 113. So if you look at this, it's like, wait a second. Within the same units, we have 113 power, -10 power. That seems to be about 120 orders of magnitude different. Again, I haven't heard anyone else, I don't hear other people talking about this. And it's like, well, we think it would be this. Oh, we have to add up all these frequencies and stuff and this. It's like, maybe I can just go into Wolfram Alpha and it's going to basically figure this stuff out for me. So it's like, by that, bada boom, bada bing. Oh, look, oh, we get like 10 to the 122 or whatever. The approximate 120 order of magnitude thingy that we have there. I'm like, oh. And, and again, this is literally the density where you would create a black hole. So I'm not sure why anybody would think something like that because if the Earth has the density of, I don't know, like copper was the density of Earth. It's like 3.6 grams per centimeter Earth density. It's people like saying, "Oh, you know all these things." Like even at like the whole from source code, like, "Oh, how did you know that?" It's like I literally just use Wolfram Alpha. I spend far too. Some people like going down Wikipedia holes. I still enjoy that. I still use that to supplement. Okay, so it's like 5.5 grams. It's this number threw me off because it was pretty close to the Planck density. What the heck is the Planck density? Planck's density is just the Planck pressure divided by c squared because it you go from energy back to mass. That's all it is. Um, so it's like you got this. It's like all right. So if we're at like 5 grams per centimeter, why would we expect the vacuum energy density or the Planck pressure or whatever we had there? It's yeah, yeah, a lot bigger. Hold on, we'll give us the calculations. Yeah, look, you even have it right there, the Planck pressure. Oh, boom. It's like 122 orders of magnitude right there. Okay. I'm belaying the point. I apologize. But it's like, these are the things where you just look at it and like, I mean, you could just look at it this way. I mean, I don't know. I don't know. I like playing with blocks, Legos, Lincoln Logs back in the day. That's that's how I usually figure stuff out. So, okay. Oh yeah, no, I used to do some. Yeah, I used to do sales and stuff, traveling around. I've been through Leominster, but yeah, no, I remember getting off at Mechanic Street. That sounds familiar. Yeah, dude, don't worry. It's like I was literally realizing I was bringing up the stuff from like Coda the other day, and like to my not surprise, I just looked at it. I'm like, I know what that means. And then I thought back to like 3 years ago. If I opened that same little thing, yes, 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 Jedi. It was literally the exact same thing. It's like it was all Greek to me. It's like I have no idea what any of the symbols on this page mean. But it's like learning any language. And in some ways it's oh God, this is a terrible analogy. It's gonna get me in trouble. It's kind of like watching, I don't know. Star Wars, Star Trek. You might have heard some things, but until you've spent some time watching, consuming content in different forms, and basically getting immersed, so to speak, in those worlds, that's the easiest way to pick up a language, or at least that's what I was taught in high school. It's like the easiest way to learn language is to immerse yourself in it. So that's what I did with all the science stuff. It's like I went from it's like, all right, spent some time in politics and then news and then modern media and stuff like that. And then eventually it's like, well, a lot of people just seem to be yelling at each other, so let me go into science. And don't get me wrong, there's still plenty of people yelling at each other, but I'm like, let me jump into this, listen to like all of Sean Carroll's biggest ideas in the universe, where he's literally, oh my God, that series is gold. That series is gold. In my opinion, um, I would just listen at work, just work in the warehouse, lifting things up, putting them down, just listening in the background. It's like, don't understand most of what he's saying, a lot of terms I don't understand, but I was immersing myself, starting to learn and learn. And then after having people sit down with me and literally several thousand hours on Wolfram Alpha, adjusting computations and going through things and wanting to pull my hair out just because it's like, why am I off by 76 orders of magnitude? Oh, I use the Planck unit with a big T instead of the small t. Yeah, yeah, yeah. If you know what it is, yes, yeah, Star Wars, yes, that one. But again, I look at this, I'm like, well, if this is the difference right there, why don't they just say that? So again, these are the things that slightly bother me, but I should let's continue with Matt O'Dowd. Sorry for the little rant. Uh, it's hey, welcome, sure, sure. Maybe, maybe that's the thing. No, the big thing is if somebody's interested. That's even at the Wolfram Summer School. That's one of the big things they said. It's like you're going to work on a project. You need to pick something you're interested in. Because if we just give you something and you're not interested, it's like you're not going to do it. That's the thing. Because a lot of people do plenty of things that they don't like to do because they have to do it. But if you have to do something, there's a little difference between doing something just because you're forced to. Maybe you still do a great job. That's totally possible. You might be a little bit more likely if you really enjoy it and you got that passion to do it. So that's an opinion. Hold on. Did I share with? I need to share with the volume. Sorry, I think I did, but sorry. See, short-term memory.
This has been called the worst prediction in physics. We don't really presume that we can predict the energy of the vacuum using current theories. The quantum field theory used to do this calculation is incomplete. It breaks down at very high energies. Now, it's generally assumed that other effects at play, at higher energies than we've tested, work to suppress the vacuum energy, but we don't know how. Perhaps you recall the recent episode where we talked about how a naive attempt to calculate the mass of the Higgs particle using quantum field theory gives a similar problem. a very large or even an infinite Higgs mass.
So, okay, if you start getting infinities and you're trying to count up all the stuff, it's like maybe there's a problem.
It's really the same issue, and perhaps it has the same solution.
Here's where my here's where my uncouthness and total narcissism comes in. Okay. So what Matt O'Donnell just said is like maybe something for the dark energy or lambda, the cosmological constant, or the mass of the Higgs boson. Maybe they have a similar answer. I'm not going to say hold my beer. I don't have beer. I'm out of coffee now. But speaking of stuff, all right. Number one. So the Higgs boson, we did a little something about this before. Let's again, I'm just going to show a naive calculation. So again, the question is, and again, this is more of a thought. Many physicists believe that the magnitude of the Higgs boson should be about the magnitude of the Planck mass. Why is it 17 orders of magnitude difference? Let's just do a quick little calculation. Let's just do the Higgs mass. And again, this is just a rough estimate. We're just taking the digits that we pretty have a really high confidence in, divided by the Planck mass. What do we got? We got 17 orders of magnitude difference. It's at least for the first couple of digits. Yeah, it's like almost precisely 17 orders of magnitude. What the heck is going on there? Okay. So one of the things that I learned from listening to Sean Carroll's Biggest Ideas in the Universe and his Mindscape podcast. He's like, oh, when a physicist, you look at different things, their relationship. Sometimes if it doesn't make sense, you square it or do something like that. I'm paraphrasing, and maybe you take the square, you do some very minor minute divided by 2 pi, something like that. Something that like you could try to intuit 2 pi. Okay, maybe there's a rotation in it. You're squaring it. All right, Pythagorean theorem that seems to explain it almost everything, so or at least many things. But let's just do that. Let's just take the Higgs mass, divide by the Planck mass, and we got to square it. Okay, what do we get here? Okay, okay, so it's basically double, but it's not one. There's at least enough information here that it's saying it's 1.05 times 10 to the minus 34. Now, again, this is most likely nothing and simply a coinky dink, but that happens to be the first three significant digits and correct exponential power without dimensions. Gotta put that out there. Without dimensions to h bar, the elementary unit of action, because the first three digits, 1.05 times 10 to the minus 34. Now it is in joule seconds, which is the reference of action. So that got my old noggin a jogging. I'm like, wait a second. So at least like the Planck mass, we know to like five significant digits. We have like seven, but there's error in the last two. The Higgs mass, Wolfram Alpha is only really putting in about three significant digits there for like high accuracy. I think it's like, what is the Higgs mass? It's like they have like 125.22 Higgs mass. Okay, so they still have it at, if we go to the particle, it should give us a little bit more. Okay, 125.18. Okay. So it's at this magnitude, uh, but just roughly, they just have it as 125. So I'm like, all right, well, if we have high confidence that we know at least three significant digits, we have high confidence we know the Planck mass, hypothetically, if it was equal to the elementary unit of action, um, maybe you could do something interesting. Because what you could also do is you take this and sorry. So long story short is you can we square this. Sorry. Well, let's just set it equal to h bar without dimensions. So we just set it equal to h bar. Divided by the reference of action, the joule second. So we're literally dividing it by the one of action. Literally, a joule second is the one within the system. Okay, this is literally all we're doing. And since we know these other things like H bar, we have it defined at 10 significant digits. We got this to at least five, going on seven significant digits. This is just in reference to this. This is literally just one with as many zeros as you could put on that. This we're uncertain. So by the power of algebra, we solve for x kilograms. Enter. Okay, it goes through. Oops, I did it wrong. Supposed to be the squared relationship. There we go. They'll give you this. So, all right, again, we're solving for kilograms. Click a duly note. There's a negative answer here too. So just maybe that's telling us something. So we're just gonna click on that, throw in kilograms. What do we get? Oh, look, it looks to be about the mass of the Higgs boson. That's interesting. Long story short is you can rewrite this whole dang thing. Rather than having to set it equal to that, you can literally just take that. Just literally get rid of all of this, and then we just do this. We're literally just using high school math here. So we're taking h bar and we're dividing by the joule second. So this is going to give us that magnitude without the dimensions. Because this is a one, the joule second, it's the reference of action. H bar is the basis of action. It's the one of action and then the reference of action. So these are both ones. I had to actually was doing during a live stream, and I think some of y'all were actually here when I was like going on the big board at the physics monastery, and I was changing my words because I'm like, what is this actually thing? Like, what is the most accurate language I can use? The most accurate language I can use is this is the elementary unit of action divided by the reference of action. So this is our base of action, and is set referring to what is the one in the system of the joule second. So we get the whole that magnitude of the elementary unit of action right there, but there are no dimensions because we've divided by its reference of action. What happens if we do the square root of that? Because now we don't need to worry about any funky dimensional stuff there because we've divided dimensions out. Oh, look, we get about 17 orders of magnitude. That's kind of around the magnitude of the difference between the Higgs mass and the Planck mass. Let's let's just put the Planck mass in here and just see what happens. Oh, look, you basically get the mass of the Higgs boson. There's a little bit of a rounding thingy there, but if anyone cares enough, you can always go check the CMS detector out of CERN. The most recent measurement of the Higgs boson mass. This is the number they came up with. So just saying, just saying. Uh, to build the Death Star. It's that reminds somebody needs to come and just remind me or just send me a message. There is a paper on doing the calculations for how much power the Death Star needed to blow up Alderaan. Like not just blow it up, but like all the effects you see in that scene. It's only like 12 pages long. And a lot of the math, it's like, okay, yeah, it's a little fancy. Heck, I might need to use Chat GPT or the Wolfram Notebook Assistant to help me set up maybe an integral or something like that. But a lot of it's like, oh, how much power did you need? A lot. A lot. Because it wasn't just like it destroyed Alderaan. Alderaan literally was went kaboom! And a very violent explosion. So I do need to cover that at one point. I know, I think Dr. Tom Crawford brought that up. I think that's his name. Okay, so we got that. All right. So again, all we did with this is we lit it. The most questionable thing here is I divided by 1 joule second. That's the biggest complaint I've gotten from folks. It's like they're not arguing that it seems to match what's there. It's literally you divided by one in a way that's weird. I agree it's weird. Because the counter to that would be like, well, that would mean that the joule or the joule second has some significance. How could that possibly be the case? Our units are arbitrary. Unless we got really dang lucky somehow. The discussion for another day. Okay. Let's go back. I know. I threw a lot of math at you. Let's get back to the video. We'll at least get to the relevant point. There we are. Spoilers that for those who may stick around a little bit longer as we finish this. Um, the claim is the solution to the vacuum energy. I claim it's doing something similar by using one squared. Again, probably nothing, but I don't know. Is dividing by one more or less reasonable than adding up infinity? I don't know. I'm not a mathematician.
One way to get both the Higgs mass and the cosmological constant down to the tiny values that we observe in this universe is for the various effects of the quantum fluctuations to cancel each other out. We know this happens with other particles like the electron, in which the symmetry connected to the existence of antimatter sort of eliminates higher energy terms in the electron's mass. The hypothetical particles of supersymmetry were meant to do the same for the Higgs, but we're having a hard time finding them.
Okay, I'm not gonna lie. I would love for folks to discover the supersymmetric particles. Why? Because then we could be talking about squarks. Because basically every particle is the exact same thing, except they add an S for supersymmetric. So an electron becomes a selectron, a proton becomes a subproton, or something like that. A quark becomes a squark. Just for that reason, I would love to see that discussed. I think something about it. In order for those particles to exist, the pop quark needs to have a mass of, I think, like 173 and a half. And right now, it looks like it's about 172 and a half gig electron volts. Um, Looking like it might not exist. Maybe it exists in higher energies, but yeah, we don't seem to be finding them. Uh, Continue.
Absent such a perfect or near perfect cancellation due to an underlying symmetry, it seems that cancellation has to be kinda random. But to randomly cancel a bunch of uncorrelated effects down to 1 part in 10 to the power of 120 in the case of dark energy really strains belief. Getting that result by chance has the same probability as flipping heads on a fair coin 400 times in a row.
Okay. So initially you hear that, you're like, oh, that's only 400. That's not like 10 to the 120. And then for those of us that play Dungeons and Dragons, and you roll a d20, and if you get two 20s in a row, that's like a 1 in 400 right there. It can happen. It usually doesn't happen. It's a sneutrino. Yes, the supersymmetric sneutrino. Hey, Sandra, good to see you, my friend. Good to see you. Yes. Welcome, Rick. Yes, we're just discussing some stuff and things. Uh, just simply going about why there seems to be such a difference there. And it's like, again, I'm not a professionally trained physicist. I'm just merely a crazy person that pretends to be a science dude on the internet. Okay. But all I know is I look at Wolfram Alpha and it's like, well, if you just put in the Planck pressure and it literally tells you. It literally tells you it's like 122 orders of magnitude different than the vacuum energy density. It's like maybe we need to add up all these different fluctuations with infinity and just go here and then go here and hope it cancels out and then come up with reasons. Maybe. Or, and again, I understand this is blasphemy. Maybe we can divide by one. And again, that goes into the question, Why the heck should that work? What are the chances that we would somehow set units to a particular value actually worked? Because the ultimate thing is whatever units we have there, our reference ones within the system are essentially some form of like a balance point or something like there. Like, why would that be the case? Again, not a discussion for here. There's some speculation and perhaps some other reasons there, but again, it's not a discussion for today. We're discussing why the heck the vacuum energy is what it is.
So, if there was only ever one Big Bang and the cosmological constant could have landed anywhere in these 120 orders of magnitude, it feels lucky that it landed where it did. Very lucky, in fact, because if the cosmological constant was much higher, the universe would have inflated so quickly that no stars or galaxies could ever have formed. And if the Higgs mass had been much larger, all matter would have collapsed under its own weight. Either way, we wouldn't have scientists to wonder why these numbers have the values that they do. We can get
Okay, so we happen to be here. And again, perhaps there is some argument for fine tuning that there could be observers like us here. Perhaps there is an anthropological argument here. It's again, for me, it's like I try to look at the numbers, I try to look at what seems to be what input, how do we explain more with less? That's the big thing. Because it's like, yes, I do plenty of random things and yeah, it's numerology. But again, I claim that numerology is numerology until it explains more with less. So that's my claim there. Yeah. Hey, Bass. Marcus comments, I see what you did there. Oh, apologies, Keishel. Thank you for joining. Oh, God, of course. Of course, I'm going to highlight that right before Kristen gets in here. Oh, God. Oh, I'm already going to hell. So, these things happen.
around this using the anthropic principle by noting that if you have enough Big Bangs, eventually you'll get one with the parameters you need to form scientists. So at least 10 to the power of 120 of them if that's really the possible range for the cosmological constant.
Okay.
Many scientists hate this use of the anthropic principle in a vast multiverse because it seems like an explanatory dead end, even if it's right. They'd rather be able to calculate the value of the cosmological constant from first principles, but there's no guarantee that this is even possible. And actually, it turns out that
Okay. So, there can only be one. Yes. Highlight. Okay. So, he just said people would like to calculate that from first principles. So, again, I don't have a beer. I don't know, but just from just from some dude just doing some crazy numerology on the internet. Again, take it for what it's will. Okay, so we got the universe vacuum energy density here. Hold on, let's go to something. Hold on, I just realized I need to actually share the window so for it to actually work. Okay, so I think it's actually changed. It was about 5.3. It depends on which. If you're using the, hold on, let me see, logical constant problem. So this guy, oh, not that guy. Small logical constant. Oh, I hate that. Guy, blah blah blah, 120 orders of magnitude, blah blah blah. Okay. So at least according to again, this is Wikipedia. It depends on what you're putting in for your numbers here. But typically, at least with the CMB and some supernova data, again, there could be other reasons for that. Maybe there is a slightly preferred thing in the universe. We'll see. And uh, again, Professor Keating had said that at least the Simons Observatory Could have the capability of potentially detecting something like that, which is exciting. Okay, so where are the values? So estimated value, and again, this is from the 2015 Planck collaboration. All right. So they're giving us about 5.35 times 10 to the minus 10 joules per meter. So that lines up appropriate magnitude, 5 times 10 to the minus 10. Okay. So you look at this and it's like, well, if some people may think, and again, I don't think there's any real reason why anybody would actually think this, but the naive calculation that Matt finally said, it's like the naive calculation is, you think it'd be something like this. Again, same dimensions, but again, 122 orders of magnitude from what it is. So you're like, huh, what could we potentially do to figure this out? Okay. So something that I've learned from Thad, John Williamson, and Rick, who was here, is sometimes looking at things from another perspective can be quite useful. What do I mean by this? Okay. So if that's the maximum pressure, let's do something like the Planck energy. Because we're looking at energy. All right. So you do energy, boom. It's going to give you this big number right here, 9 point, blah, blah, 1.9 times 10 to the 9 joules. Okay, blah, blah, blah. And it's equivalent to about the Planck mass, or is equivalent energy wise to the Planck mass. It's like, all right, what if I flipped it upside down? Literally one. Look at it. Okay. And then I kind of looked at this and I'm like, oh, that seems strange. Now, again, it's in completely wrong units and everything. It's in reciprocal joules, but I'm like, wait. 5 times 10 to the negative 10. 5 times 10 to the negative 10, that seems to be the at least the first significant digit and the correct magnitude of vacuum energy density. That's weird. So that's why when I was saying, does it make sense? And this is one of the reasons why I wanted to go to the Wolfram Summer School is to see if I could find a better answer than because it works. I haven't really been able to do that yet. I've gained some knowledge from a whole bunch of sources about why this might be the case. Still speculative, but the answer may be I don't know. So, long story short, is this is energy. This is expressed in joules. If I want to get energy back out, here's what we need to do. We just put in the energy joule. So, literally, we're putting in one. We did the joule second for the Higgs mass to cancel out the dimensions of h bar, the elementary unit of action. So now we're taking the joule. So basically, the Planck energy is the one of the one of energy. This is the reference of energy. We divide the reference one by the one itself. It's giving us, okay, so it's giving us of magnitude there, but we still need it there. So we square one. I know. One squared. Okay, now it's giving us energy, but we're still off. Okay. Now here's where we just get reckless abandon. Long story short is I could have done this calculation a while ago. I looked at it; it was just so crazy. I'm like, how the heck do I justify any of this? I found it through another mean, uh, literally doing actual like more mathematical arguments and stuff. But all right, so it's this is expressed in energy divided by meters cubed. Okay, meters cubed. That's how we're measuring it, right? This is so stupid. Oh, look, we're almost there. We're almost there. Is there some term we could use to get us the rest of the way there? Um, I won't bloviate the point because we've been going for over an hour. Long story short, after searching for all different things, part of the justification was when at one point I think if one believes that dark energy or whatever that might be is the cosmological constant that tends to infer that there may be some curvature going on. Well, pi is basically a constant of curvature. We've got three dimensions here. Let's just do that by three. Now, that's not the reason for it. This is just the best fit that I was able to find as far as simplification. But you do that, and all of a sudden, so it's like, all right, so this little expression here, it's literally pi divided by three, which coincidentally is like 60 degrees, uh, divided by the one of energy squared, divided by meters cubed in the Planck energy. Okay. 5.35 times 10 to the minus 10 joules per cubic meter, or basically approximately the universe vacuum energy density, which we go back, where was it? Okay, at least the first couple of digits, 5.35 times 10 to the minus 10. 5.35 times 10 to the minus 10. And again, there's some other significant digits there, but those others, it's basically, if you look here, the kilograms, it only has three significant digits. There's only three significant digits. I mean, if you could just do that, that might be floating points, or maybe they just have a better measurement there. Who knows? Um, but, oops, sorry. The long story short is, okay, is this first principles? I don't know. I'm using units within the SI system. The most controversial thing that I'm doing is instead of putting the Planck energy upstairs, because that's what you're doing with the Planck pressure. You're just taking the Planck density, which is just Planck mass divided by Planck volume. And then you're just turning that mass into energy, and that's where you get the Planck pressure from. Under pressure. Uh, so again, the most controversial part of this is I'm dividing into one squared. And again, the feedback that I get is, well, that would mean there's some significance to the joule. My best argument this time is, well, it's the reference of energy. If you want the Planck energy to mean something, we express it in joules. If the joule doesn't mean anything, so that's not the most satisfying argument because I could totally see it being a different way. Now, there are other arguments, but again, like I understand the core of that. It's like, well, that would mean there's something meaningful. It's, I mean, come on. What are the chances that we would somehow settle upon a system of units that made so much dang sense that literally our reference from seemingly arbitrary things we got right? It might be right up there with us actually being here because you follow a standard history of the universes. You'll conventionally hear it. It's like, all right, how did we start? Cosmic fluctuations. It's like, all right, so we're already hand waving here. So it's kind of like wizardry. They're casting a spell. It's like, all right, cosmic fluctuations. And then stuff started expanding. Oh, at the speed of like, no better. It was going super luminous. It was going faster than the speed of light and everything. But I thought that was the limit. Oh, no, 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 no. That's only for the stuff in the universe. Universe itself getting under. It's like, okay, well, that doesn't, okay. Yes, yes. And then we happen to find ourselves in a galaxy that doesn't seem to be too active right now, around a star within the quote unquote Goldilocks zone. Uh, it gets better. It gets better. Not only were we in a potentially okay place to form, we then had a planetoid sized thing that crashed into us, maybe gave us enough water, happened to give us a very large moon that had provided different electromagnetic or whatever gravitational effects there that happened, something life we got here. Okay. I mean, statistically, that sounds like a miracle to me. Who knows? Do miracles strike twice? I don't know. Let's get back in here. Okay. Oh, hey, Matt. What's going on, my friend? Where are we? Da, 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 da. Okay. And Sandro's talking about some of the stuff he was working on, electron, the entire. Angelo filled with heat space on the particle detect as a cold gravitational component of the electron. I mean that would be interesting. I mean, it would be more interesting. Again, we're gonna need some more data on that. Uh, yeah, no, I mean, if they could do some high quality experiments and everything, it would be an interesting thing. Hey, welcome, Six. Good to see you, my friend. Yeah, we're just going over some different stuff and things. I was ranting about I don't know, the standard ways that we come up about things. It's like, all right, you get your quantum fluctuations, we go through, bada boom, bada big bang, yada yada, something something, and then we happen to be here and remotely viewing and communicating with each other. It's like you just take these words even just separately, it kind of seemed like a miracle. It's just, and again, that's an opinion. People's definitions of fundamental stuff and things may vary, but yeah, that was see, this in and of itself. Bother with more math right now. Let's go a little bit more in the video, just because we happen to be here right now. So let me share. Let's go back to. Ooh, where did we put that? Oh, there we go. Go back to Mr. Matt. Oh, God. Okay, so we're not going to finish this video. We'll just get to basically made the main point.
That we can at least constrain its possible value by using anthropic arguments. So, back to Steven Weinberg's paper. Anthropic bound on the cosmological constant is aptly named. In it, Weinberg uses anthropic arguments to calculate the value of the cosmological constant, or at least what it should have, if its value in our universe results from a selection effect in a multiverse of many different cosmological constants.
Okay. So in a multiverse of many different cosmological constants, it's like, okay. I mean, if that comes out and we're just trying to do some probabilistic thing, maybe that makes sense. Um, I don't know. I don't know. For me, I'm just like, just kind of doing what like Thad taught me. It's like, all right, now whether or not you agree with Thad's method there, um, if one were to attempt to do something of the scale and level of potential like craziness that that was, like if one were to attempt to do that, how would one go about it? And as far as I can see, I'm like, well, the two postulates you need are one, math works, two, logs are useful. Basically all you really need. Um, and there are there's actually some other interesting things. It's we'll see. We'll see what happens. But let me see what was folks saying here. Da, 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 okay. Sam was talking about. I think. And again, I'm not going to pretend like I understand what the Schrodinger equation is. It's more like, all right, does this stuff, does these things? We can measure these parameters. It's like, all right, this particle or however we're going to set up, it's doing some stuff, going to be in some things and the measure of stuff and things. Yeah, I don't know. Because part of the electron we detect is a vacuum. Okay, I think they're saying, what is it, like the bare or the dress mass or something like that. See, I thought that came from like the Higgs or something. Uh, but then again, it's the interesting thing is even Stephen Wolfram at one point, folks were saying, oh, well, there's like, oh, we believe we lived in some ether and stuff. And then Stephen Wolfram's like, well, basically, we do live in like an ether. It's called the Higgs condensate. So at least that's according to standard physics. There's something that is like uh, superfluous. No. Diffuses. That's the word. See, I can still do words. It suffuses all of our realm as we know it. So it's like, now we don't say the word ether because that's like the book, but no elephants, but no ether. Why? It's a five-letter word, and we don't like those words. It's totally not the ether. Rick is commenting, unlimited calculus. Whoa. All I know is I thought that's a play on because it's supposed to be infinitesimal calculus. It's like we treat something as zero, but not quite. It's an infinitesimal. It happens to be a supporter of that as well, and some form of discreteness, so to speak. Um, how discrete could it be? I don't know. I guess it would have to be redonkulously small. What's the exact definition of redonkulously small? I don't know. Yes, discrete. Now, people have many ideas about that. I've seen some ideas that I am more fond of than others, and yes, yes. Let's continue a little.
The argument goes like this. Assume there are many universes with different cosmological constants, and only a small fraction of those have values amenable for the development of life. We are, of course, in one of those. This is the standard
Oh,
argument
we're
of the
biased.
anthropic principle, but Weinberg goes much further. He uses this argument to actually estimate what that constant should be for this universe.
Okay, so now they're making the argument of observers, and again, maybe I just tune these things out. It's kind of like, oh God, was I think Robertson Earnhardt. I think he had on the Tim Mon. Oh God, David. I think David Albert. I think it was his name. He's a philosopher of physics, and he was talking about. He's like, all right, so if in this version you have like Captain Kirk and he's wearing a green shirt and a red shirt and everything, it's like I started watching Star Trek. It's like maybe I'm just throwing away those ideas too fast because it's like maybe I just don't understand them, or maybe it's just not satisfactory to me, or probably just my inherent bias there. Uh, so I think he's going to go into, well, because I know Professor Carroll at one point he was saying, well, if we had observers and he's doing the calculations and stuff, it's like, why? I mean, I don't know. Isn't that kind of a human bias to say, well, it obviously needs to be us? Maybe that is a good argument. I don't know. It's who knows? Maybe the creator was like, I want to see some cool, interesting humans and all the drama they do. It's like I don't know. I wasn't there. Uh, no God nor prophet. I'm just a crazy person on the internet. Let's get back to an actual scientist.
And the key to doing this is the use of the principle of mediocrity. It says that if an object or phenomenon is randomly selected from a collection of various categories, it is statistically more likely to originate from the most numerous categories rather than from the less common ones.
So go back here for a second. All right, that sounds terrible. So literally, the principle of mediocrity, at least the principle like least actors, we're minimizing. So what's it? Nah, just mediocrity. It's couldn't you just say minimal complexity or just Occam's razor or something like that? It's uh, it, largest selected, blah blah blah. Okay, so it's going to be whatever the most common thing is from the most numerous category rather than the less common one. I mean, that's isn't that just one of those duh things? I don't know. I guess I am mediocre.
So we can divide up possible universes into categories based on the size of their cosmological constant. Many multiverse generating theories predict a fairly even distribution for this value, what we call a flat prior, meaning there are more categories with cosmological constants much larger than the tiny one in our universe.
Okay, but okay. See again, it's like if this is like 10 to the minus 10 and this is 10 to the 120, why are we only showing this? Shouldn't we have this arrow all the way there and shouldn't we be in the center there? I mean, again, it's unless this is an extremely good unit system. I don't know. That's that's kind of like one of my complaints here. It's like, well, why should that be the case? Um, I understand. I basically am arguing from a position personally that yeah, our units we probably seem to have gotten something very right. again, I am very biased because it helps me do these little calculations where it's like, all right, well, if there happen to be some significance to like the joule or the joule second, it's like, I don't know. Oh, sorry, I'm not, forgot I wasn't doing the different thing. God, here we go, window. I'm just saying that if I can divide by the reference action of one, calculate basically the Higgs boson, mass to at least what the most recent measurements are, at least within the error bars. Uh, and then if you let me square one and then just divide by other stuff, I don't know, it appears to be the vacuum energy density. And again, God, I mean, if there was some significance, that would kind of be a miracle. Very, can you tell I'm a little biased? But let's let's continue with Matt.
The mediocrity principle tells us that if we choose a random universe out of the entire multiverse, it should have a non special value for that cosmological constant, so it should have a large one. But if we choose a universe that we know.
Okay, Brian. Let's see. So are we asking some of the constants? That was earlier in the videos, probably like I think 5 or 6 minutes in. Matt was saying that I think a lot of physicists they would like to calculate things like the Higgs or the vacuum energy density or something from first principles. Now, what are first principles? Actually, that's a good question. First, is there something here that I don't? The fundamental concepts or assumption on which a theory, system, or method is based. Okay, so your primary things. My my big thing is, well, I'm just using what's in SI. I'm just using SI units. The most controversial thing that I often do is I'm using one, the references for those things. Now, maybe it gives you pretty good agreement with the data there. Um, yeah. Long story short is this is a video specifically about is there a simple proof for the multiverse, and they're going over Steven Weinberg's uh, his paper, basically trying to make an argument for well, maybe we live in the multiverse, we just happen to exist here, so we're able to talk about it, and they're running some statistical probability and everything, and we're kind of like delving through that. A couple of the things that they were talking about earlier was where are we at? 950. So the four things they were talking about here was why things seems finely tuned, quote unquote. So basically, you got the binding energy of helium. If that were to wiggle a little bit, yeah, things would be you basically throw everything off. Stars and stuff wouldn't be able to do their thing, or you really wouldn't have the other elements. Nuclear energy level of carbon 12. So yeah, stars being able to produce and go through their chain and everything. So I think these things are kind of related to like the fine structure constant and stuff. That's why it's like, oh well, these things aren't fundamental, but the fine structure constant relates to all these different things. Now, again, I'm not a chemist. I might just be speaking straight up blasphemy there, but I think that has something to do with the electromagnetic coupling, and I think that is kind of how we get out. So, something about the fine structure constant, okay? Something about the mass of the Higgs boson, and oh, sorry,
Smallness of the strength of gravity compared to the other
the strength of gravity compared to the other forces. So, perhaps all we need to do is figure out why the fine structure constant is what it is, the mass of the Higgs boson is what it is, and how that gravity works. Is that all? Yeah, and again, this almost goes into one of those things where, okay, that's all we need to do. I mean, maybe we could do that at some point. I happen to be of the persuasion that I think we can do it. Now, the chance of coming across solutions to the fine structure constant, the mass of the Higgs boson, and whatever the heck the gravity is, I mean, I don't know. Is that another miracle? What are the chances that miracles would strike thrice? I don't know. All right, 9:50. We're getting there, folks. We're getting there.
that we know has observers in it, we add an extra constraint. We're now selecting from a subset
Oh,
of
hey,
the
Charlie.
multiverse with a much smaller cosmological constant. But besides the anthropic constraint, the cosmological constant in this subset should be as non-special as possible within the constrained range.
Okay. So what I'm getting out right now is within the constrained range, if we think there could be a multitude of potential universes, so to speak, whatever that might be, um, and we happen to exist in one. So, okay, number one, it's like if we're here to talk about it, well, we seem to have the capability to exist. We happened to be here. We happen to be talking on the internet, going through all these things, remotely viewing. I am remotely viewing a video posted by Matt. Y'all are remotely viewing me or temporally in the future. I mean, this is basically magic. Uh, or at least a few hundred years ago, or actually probably not even that long ago. This is literally magic. I mean, who would have thought it's like, listen, I, I, I hold up a little tablet. I make some gestures. Food appears at my doorstep. Who predicted that? Maybe Star Trek. But all right, where are we at now? Let's just go through here. Yeah, is time or the passing of one moment to another moment a constant? That's a great question. As far as I know, we progress forward at 1 second per second. That's not a satisfactory answer. As far as we know, the general minimum of time to our knowledge is Planck time, 10 to the minus 44 seconds. Now, full disclosure, if you're going to go more like the Wolfram model here, the elementary time is like about 10 to the minus 100 seconds or something like that, at least within that framework. Um, and again, that's if we're getting sub-Planckian there, that's basically beyond physics as we know it, so to speak. I'm using the quote unquote because people have different opinions about things, and that's fine. It's follow the evidence. So, as my old man, God rest his soul, used to say, truth is the ultimate defense. Apparently, Mike McCulloch liked that on Twitter earlier, and he retweeted it.
So says the mediocrity principle. In other words, it should not be a lot smaller than it needs to be to allow observers. If the cosmological constant is much smaller than is strictly needed, that might be taken as evidence against the anthropic explanation. Okay, the next step then is to calculate the maximum strength dark energy could have before.
This comment just tuned in. Could use a stiff hit of the Higgs. The Higgs condensate always talking right before you got here. Um, at one point, Stephen Wolfram was in, I think it was with Professor Keating. At one point, Professor Keating was like, oh, people used to believe there was something like an ether. And Stephen Wolfram's like, well, there is effectively a thing like the ether. It's called the Higgs condensate. And it's something that, according to physics, as we know it again, seems to suffuse all of our universe as we know it. Okay. And again, but we don't say ether because it's again 5 letter word, but no ether, superfluid, space time, the medium. Those are fine. Ether, no, 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 no. Why? Because there's some experiment that ruled out like a non-kinematic ether. So we're like, but no ethers. It's maybe some of those little technicalities. It's like, wait a second. So maybe there's a kinematic ether. Shh, I might have gotten that wrong. It's either one or the other. Uh, but again, we did that experiment like 100 something years ago. I'm sure it's not like our technology's gotten better. I'm sure some other folks have done it. Feel free to turn me on. Yeah, and Charlie, we were also going over there's a point in the video where Matt was saying it's like, well, if we could solve these things, and they're talking like, well, we had the previous episode on like the Higgs boson and stuff, so it's probably somewhere over here, maybe. Yes, yes. I wonder what my algorithm is loaded with. Uh, so, but basically, the thing is, they're talking about why the naive calculation, the dark energy is what it is. So we'll just bring that down. We'll just bring this back up for real one quick second. Uh, but basically, he was saying that maybe whatever the solution to figuring out how to calculate the Higgs mass might be a similar thing to figure out the dark energy is. It's like, and again, I don't have a beer or anything. I just finished my coffee, but I'm just saying if one is allowed to divide by one joule second, the elementary unit of action, multiply it by the Higgs mass, Planck mass. Well, we get 17 orders of magnitude difference multiplied by the Planck mass. Oh, look, it looks like the Higgs mass right there. Are those 17 missing layers of reality? Is I think Matt O'Dowd put in one of the videos and the title there. So I mean, it's a great title, but it's like you're just talking about orders of magnitude, like because we think it should be closer to the Planck mass. Okay, but I don't know. All I did was literally just take the root of action, of taking the one of action divided by the reference of action multiplied by the Planck mass. I'm sorry. I didn't do the quadruple integral over all the sums of infinities to calculate all the things. I'm sure this is just strictly a coincidence, and they're not going to continue to measure digits that match with 8 bar. I mean, that would be weird. Oh yeah, and then the universe vacuum energy density. Hold on. So we literally, this guy. It was this guy. All right. So if we take the Planck pressure under pressure, we can see that. Wait a second. The Planck pressure. Oh, look, it's 122 orders of magnitude greater than the vacuum energy density. Now, again, to Matt O'Dowd's credit, in this video, he said if we do the naive calculation, okay, so it basically, if you just throw in Planck units, or you calculate up to some energy cutoff, which is basically the Planck mass or Planck energy, depending on how you want to express it, so the Planck pressure. If you hit this pressure in a given volume, you're uh, you're basically going to create a black hole, as far as we know it. Why? Well, because if we just divide this by c squared, you get the Planck density. Oh, look, the Planck mass density. Oh, okay. What's that? It's just Planck mass divided by Planck volume. That's all it is. And again, a lot of this, it's a lot. I just happen to learn this stuff in a particular way. It's I'm terrible at learning things and then knowing that things are going to change and then having to relearn them. I remember when I was working at an internship at Putnam Investments at what? I mean, an internship at totally some indescript financial institution that totally didn't get in trouble for market timing back in the 2000s. That's better. Uh, yeah, basically, we were still using like the DOS prompt screens, and they were kind of teaching us on them, but they were literally swapping over to just like the visual, like standard Windows based screens and stuff. And I'm like, well, we're going to be swapping over soon. So it's like, I didn't really learn the DOS things. And it's like, oh, just talk on the thing to the customer. It's like, but I'm still having trouble navigating the screen. It's like, this is an internship. We're just going to base you on your call center metrics. And I'm like, wait, this supposed to be a passive failure. You giving me a C just because I wasn't great on the phone with people? F this. So I got them to retroactively change everyone's grade to just pass fail. Uh, because it was BS. It's like, what? You didn't even tell us this was a thing. So I'm sorry. I'm ranting about things of the past. Where are we again? Okay, let's. I'm sorry. I'm sorry. I'm just. I'm right. Oh, the whole thing is if I can divide by one or if I can square one. So if we could square the joule, the unit of energy, if we square that, we divide it by the Planck energy because the whole, okay, this deep lore just goes down this way. Basically, all we got to know is, according to the best of our measurements, vacuum energy density is about 5 times 10 to the minus 10 in magnitude of energy density. Okay. If you do 1 over the Planck energy, you get 5 times 10 to the negative 10 in the wrong units. In order to make those units correct, basically, you literally just take the reference of energy, the joule, you square it, you divide by meters cubed and the Planck energy. Get really close. If you want a term to best fit it, divide by 3. Something, something curvature. This is basically just matching the data, doing the most naive thing possible. There was a more detailed explanation and argument for this, taking the geometric mean of these things when I was doing a different calculation, but this is just a computationally reduced form of it. And again, it looks so dang silly. Oh, look, it's kind of cute there. It's okay. I'm sorry. Oh, let's get back to the video, and I can catch up with the chat. I'm so terrible at these things, but God, we're almost there. We're almost. We will get there someday, my friend. See, it takes forever to review a video. You got to do commentary because you want to do fair use, and again, if I just sit here and play the video, it's like, what the heck's the point in that? Oh, look, oh, I'm getting watch viewers and stuff. It's like you might as well just go watch the video. It's I'm not looking to just take time away. That's why it's like it's listed there. Please feel free to watch it. This stuff interests you. Continue, sir.
or life becomes impossible. The principle of mediocrity says that dark energy shouldn't be too much smaller than that. Steven Weinberg did this by figuring out the maximum dark energy strength that would still allow life-supporting structures to form.
Like
We
it's
know that
infinity.
stars and galaxies formed when
A
overdense
lot.
regions of gas and dark matter that filled the early universe collapsed under their own
Maybe n
gravity.
plus one.
But
I
this
don't know.
gravitational in-pull had
Welcome, my friend.
competition. The expansion of the universe meant that over time matter was thrown
What is
further
a
and further
singularity?
apart, and beyond a certain distance, gravity
Some may
becomes
say when
too
God
weak to
divides by
drag that
0.
material back together. It was this balance between in-pull and gravity.
Okay. A singularity. Okay. These are good questions. Now again, I'm not going to pretend like I have the answer. I can say some words, but again, it's I can say words. If I say words, doesn't mean it's true. My personal thought is the best explanation I have is, well, Rick had been talking a little bit earlier about like this discreteness. What if infinitesimal calculus? What if there was a discrete? What if there was an infinitesimal? What is the infinitesimal? I think Thad had recently started talking about what he thought that was. I think it's if you're interested, that I think it he talks about maybe on the Physics Monastery Patreon. I know he's editing some videos and stuff right now. Um, my best solution is, well, what what if there was a minimum? Number one. Uh, Number two, if you really need your singularity, coincidentally, the complement of the hyperbolic figure eight knot, that figure eight knot that's in that little torus shape with just like the little figure of eight going through it, technically, it is also characterized by its unique, again, this is just according to Wikipedia, its unique 0, 0, 0, 0 point. For those of you that counted to four, there were four zeros there. So again, I'm not a mathematician, but I'm like, well, if you're going to do a coordinate system, you had 4 dimensions, supposedly, because we live in a four-dimensionalish or 3 plus 1 or 1 plus 3 uh, dimensions of space and time or time and space. Uh, it adds up to four. Uh, I'm just saying it's like, but that's essentially what everything else wraps around. So if you really want your infinitesimal, you really need your singularity. It's like, well, that's technically a singular point, I think. It's very often, I think they'll say a critical point or something like that where it's ill-defined. Um, I'm sorry, I don't have a better explanation than that. Continue.
An outpushing expansion that determines the largest sizes of structures that could form. In the case of our universe, that's galaxy clusters. In our universe, dark energy started to dominate relatively late, kicking off the accelerating
That's a
expansion
fascinating
6 or 7 billion
question, some
years ago.
person.
But importantly, after the universe
I'm just
had
going to say
already
stay tuned.
built galaxies and clusters. But if you dial up the strength of dark energy, then it starts to dominate the universe earlier. And if you dial it up too much, then the accelerating expansion starts early enough to mess with galaxy formation.
All right, Charlie commenting, what happens if time exists inside the event horizon? Well, according to what I've typically heard, and again, take it for what it's worth, I'm not a professionally trained physicist, time technically ends once you get past the event horizon. If there was time, so to speak, going on, it, my best just default, my mind just instantly goes to, well, at that point, you probably create a new universe, so to speak, or a new realm would probably be a better term, because just all I know is when you take radius of observable universe, you take the mass of the observable universe, and you divide it by like the radius. Long story short is, if you take the mass of the observable universe and you were to cram it into a black hole, you essentially get a black hole the size of the observable universe. Even when I do my little numerological things trying to calculate what the mass bank, so to speak, of universe might be, if you throw that number in, you get a black hole that would be the size of the maximum size of conjectured universe. Uh, so that seems to be a thing, which is interesting because if we were inside a black hole, then there seems to be time in a black hole. There seems to be a progression of events. Now, are we characterizing time in the best way? And probably not, because I mean, we're observers like us. We're not living on the Planck scale. And oh god, I'm going to have to do that project. But what observers like us might see, it's Stephen Wolfram just put out a piece. I would actually personally, now again, you don't have to, don't listen to me. He actually just put out a piece about, he was discussing, and even when I was at the summer school, we were in line for lunch, and at one point he's like, listen, I want people to be able to direct their effort in useful directions. He's like, I get all these people sending me ideas and stuff all the time. He's like, very often they're basically just using high school physics and stuff. And he's like, it's sad. I'm like, well, there's got to be some good ideas in there. He's like, because I'm like, all right. I was looking at, I'm like, all right, statistically, if he gets like 600 emails a day, but it's like, if he's getting all these emails, statistically, there's probably going to be a diamond in there somewhere just because it's like if you have enough folks around, that statistically things will happen. But again, from his perspective, he gets all these emails, and if many of them are just kind of, your perception is going to be like basically for folks out there that have some ideas or a particular theory, so to speak. Stephen Wolfram did just write a piece on that about ways to perhaps channel your ideas or ways to go about actually like refining them, things that one could do, because he's like, there's a lot of people out there that like they have passion in something and they really want to see someone. I know there's some folks in the audience here, um, and there's always going to be different levels of refinedness and stuff like that. And again, it's like one of the things I think he talks about is when you find something, one of the first things you want to do is look for it, because it's like occasionally, oh, hey, I have a calculation. Oh, yeah, yeah. See, this was well established 50 years ago. Or it's like, oh, well, Maxwell discovered this like 160 years ago or something like that. It's like, oh, okay, it was new to me, but one of the big things is it might be very exciting, but is it new? Now, sometimes there might be a restatement of certain things, but yeah, it's he has a piece out. He put it on Twitter. It's just Stephen Wolfram writing. Just search Stephen Wolfram blog and you'll be able to find it. Uh, we're getting there. We're getting there.
You can calculate a pretty straightforward limit to how strong dark energy can be to even get proper galaxies. So let's add one more factor.
I like to say the
Clearly, we
medium,
need
Charlie.
stars to live,
Speed of
but we
light
do also need
in the
galaxies.
medium.
In order to have planets,
Not
multiple
stating what it
generations of
is.
stars need to have existed prior to our own, because those earlier stars created the elements needed to build planets. So we need star-making factories, which means galaxies, or at least small ones. For example,
Okay. So we need galaxies. Okay, so we need star-making things. Are there any? If I'm getting ready to do another calculation, yeah, I won't bore you with it. Long story short, there's a calculation you can do. Okay, there's certain levels of zaniness where it's like, okay, I'm claiming that it's like, all right, if you allow me to divide by the reference of action, I can do a cool calculation. And to be fair, for Dad's calculation, that the claim is again, these are claims. These are claims. Uh, to technically calculate something like the fine structure constant, or at least its amplitude, you need to divide by kilograms in order to dimensionally negate the dimension of the Planck mass. Because otherwise, that shirt that I wear is dimensionally inconsistent. So that would mean that there would be something significant about the kilogram. Why the heck might that be the case? Again, a discussion for a different day.
a globular cluster with 1 million stars might be enough. Weinberg calculated that the maximum amount of dark energy for which such systems could form is around 500 times the energy that is in matter, if extrapolated to the modern era. Now,
Maximum amount of dark energy for which systems could form. So 500 times the energy in matter? Oh, because matter is like 5% of the stuff. So if you did that, that'd be 50. Blah, blah, blah. Okay.
the true value is that dark energy is about 2.3 times larger than the energy in matter, but 2.3 is quite a bit smaller than 500. So
Well, so long story short is they're trying to figure out in the realm in which we live of, and if you're trying to just do a likelihood, let's say if we did live in some multiverse, so to speak, uh, we just happen to be in one of the universes, and there's all these different other universes, and we just happen to be really dang lucky. Number one, again, if that was the case, that seems like a miracle. I don't know, could we have a miracle 4 times? That's that's getting up there in the Hail Marys, man. It's sorry, I'm sorry. Let's see. Uh, oh, that's right. If we had supersymmetric particles, it would be the Shigs mass. Uh, Brian's commenting spatial forces, Planck's constant, and possibly something to do with frequencies. Ooh, ooh. See, that's the interesting thing. And there have been folks talking about that because I had a discussion with that at one point. And apparently I said something and it's like, and again, I'm not a professionally trained physicist. I don't have a PhD and stuff. But my general understanding is when people talk about quantum field theory, it's like, well, you have some frequency oscillation. It's like we have the electron field, we have the muon field, we got all these fields for our elementary particles. It's like you get a field and you get a field, totally like Oprah and stuff. Even though it's like only 17, that'd be 17 wallpaper groups in mathematics, and there's no relation there. But the thing is, if you're looking at that and you're like, well, you've got all these fields, and these have like frequency oscillations. Oh, it's an oscillation in a field. And it's like, well, there is this thing called the Planck frequency. It's literally just 1/Planck time. And so basically it's the maximum frequency. I'm like, well, if these are all frequency oscillations and things, well, Planck frequency is like 10 to the 43. It's much greater than all those other things there. So I'm like, maybe it just lives within the Planck frequency. And this is something Fractal Woman had on. I think it was John M. something. Oh, I always forget his name, but I heard that from him, and it's like, okay, well, what if this is something that we have within our base units? Could it just live in there? Do we need all these different fields, or could these just be, I don't know, little subsets there? It's again, take somebody smarter than me to figure this out.
So from this calculation, our universe still has an unusually small cosmological constant compared to the set of all universes that could have produced life, for
That is a
instance,
crazy
galaxies.
one.
A couple of things here. First is that this brings the chance of our cosmological constant being so small down from 1 in 10 to the power of 120 to 1 in 200, which is a huge improvement. By adding the anthropic selection, it brings the random chance hypothesis into the realm of possibility.
Okay. So so basically, if we were to assume that there was some selection so that observers like us could be here, it strengthens the argument. Because otherwise, if it's going to be all those different things, I mean, maybe. Like I tend to think, like Dad wrote a book called "The Simplest Universe." That sounds like a good a good reason. Because we're gonna say the principle of least action is guiding. It's like, well, just some principle of, I don't know, minimalness or some something like that. I don't know. The principle of mediocrity really bothers me. It just it's like, yeah, I feel like the mascot for universe at that point should just be Eeyore. It's like, oh bother. I'm sorry. I'm sorry. I've been following Paddington Bear on Twitter. I realize that's not Pooh Bear, but they're bears for kid shows and stuff. So okay, the Planck spring constant is crazy, just because that's mass divided by time squared. Um, like 10 to the hundreds. No, it's 7.488 times 10 to the 78. How the heck do I have that memorized? I I'm pretty good at remembering the first couple of digits and exponential powers, or at least approximately close to different things. I have like a semi-videographic memory. I don't remember all the stuff, but it's like I remember certain parts, chunking them in my mind. That's the only reason I kind of like notice any of these things. But the reason why I know that to at least four significant digits is because if you take, and again, naive calculation for the quote unquote mass bank of universe, and or basically just relating the mass of universe divided by the Planck mass. Uh, I'm going to show this calculation just because I did. This is probably part of the strongest argument I have about maybe why there's something to it. Uh, so it's the Planck spring. Yeah, let me see. Well, does it come up as Planck spring constant now? Planck spring. Don't think it does. Maybe it does now. It should come up spring constant. No, it's just giving Planck constant. So just we just checked this out. Spring constant. We're looking for a physical quantity. Mass divided by time squared. There's a two there. Excuse me, negative two. That just means it goes in the denominator. So we just take Planck units. Like mass question. No, that's a good question. Huh? Planck time squared. Boom. 7.488 times 10 to the 78. Okay. Spring constant. All right. So this is the Planck spring constant, or at least in Planck units it is. Okay. So let's duplicate this. So if you just do the naive thing, it's like, to be fair, this is just a way to computationally reduce something that I first saw from Salvatore Pius, and then Rick had shown when he came out to the monastery. So I'm like, oh, maybe there's something here. So let's say hypothetically you're trying to solve for a massive universe. God, there's no way you can do that. So you're going to solve for X kilograms. How the heck would you go about this? Let's just relate it to something else. How about, oh, what's the one of mass? Mass. Okay. So I'm going to set that equal to, what could we set it equal to? I don't know. How about we do the naive thing? The reference of length, meters, divided by the one of length, the Planck length. And let's square it because we like to square stuff. What do we get? Yeah, an absolutely ginormous number. And we are solving for kilograms. We literally just tag it with kilograms. Okay. So it's giving us that. So no, it rounds up there for the fourth digit. So go over here. Give me more digits there. So the long story short, it's like 8 times 10 to the 61 kilograms. So I'm just going to turn that to 1 and then kilo over there. So what is this? It's probably like 100 million times. Yeah, it's like 100 million times the mass of ordinary matter in the universe. Okay. If you look at what its energy is, though, the corresponding energy, 7.488 times 10 to the 78. Wait a second. 7.488 times 10 to the 78. Is the spring constant equal to the total potential mass energy of universe? I mean, like, is that what's balancing it out? I don't know. I'm sorry. Basically, that is a reference just because I'm like literally squaring meters. So the difference between them is literally meters squared. So did I even? Oh, I need to go back. I need to go back and share the audio because I'm terrible. Uh, I think we'll cut it off in a couple of minutes just because we're almost there.
Still, if the anthropic argument doesn't fully solve the problem, it's not exactly a parsimonious solution. The mismatch gets
Mm.
worse if we update some of the observations that went into Weinberg's calculation. He used our most distant
Okay, so we
observations of
can't go
massive
infinity
objects to
small.
determine the maximum time allowed to form massive structures. In 1987, those were quasars that existed when the universe was around 10% of its current age.
Yeah, technically, the Planck units are derived units. Um, right now, they're limited by basically they're the most Planck units, and again, use a combination of h bar, the elementary unit action, c, the speed of light in the medium, uh, vacuum, whatever you want to say, the Newtonian gravitational constant, and then Boltzmann's constant. And then you got to use the electric constant to get a unit of charge or current. So you need to have epsilon naught in there. When you see a funky looking E with like a zero there, that's like the electric permittivity constant. Um, but basically, most of the Planck units are limited by our knowledge of big G, the Newtonian gravitational constant, because I think we have that to about 5 significant digits. Um, the mirror, it's a difficult thing to measure because it's like they were saying, it's much, 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 much smaller. So until you get something like, I don't know, like 10 to the 26, 10 to the 28, whatever kilograms Earth is, yeah, I can jump up and I pretty much come down. Uh, it takes a lot to have an effect. Uh, yes, cool.
But we now know that there were massive structures much earlier. For example, the James Webb Space Telescope has found galaxies at around 2% of the universe's current age. Those structures formed in an era when dark energy was truly negligible, indicating that dark energy could be quite a bit larger than it is in this universe, while still allowing at least some galaxies to form. But there's another refinement to Weinberg's calculation that can make sense of this. The way Weinberg used the mediocrity principle was to say that we should be in the most typical type of universe that can form galaxies. But a more powerful approach might be to apply the mediocrity
Mediocrity. Oh, principle of mediocrity. What else we got going on? Multiple singularities. Oven mitts horizons. Hey, Morgan. Let us see. What do we got? Blah, blah, blah. On around the donut shape. Blah, blah. Ooh. We'll start on ice machine. Well, I do like ice cream. You need a gravitational black hole, the whole and everything. Well, that's. I mean, if we're gonna say that most galaxies, as far as we know, here's the crazy thing. I still even remember growing up where it's like, well, we believe there are like supermassive black hole things in the center of every galaxy. But even when I was growing up and learning about these things, even within the past probably 20, 25 years, there wasn't really the general gist of what I got is people typically thought that because it's like, well, that makes sense. But it was like we believe. Now it's like we believe that unless something like scattered or something like pieced out there for some reason, we believe basically there's like a supermassive black hole in the center of every galaxy. Uh, that seems to be just a fairly commonplace thing. So it's almost like, oh, it's almost like an anchor point or something. It's like, I don't know. There are things that even more recently that we've kind of gone through. I don't know. Oh, the Kibble balance. Okay, so the Kibble balance is basically that's that is used to measure mass. The gravitational effect. So you do need to calibrate. I'm pretty sure most gravity things. I think they still use torsion balances. I didn't study the gravitational constant. Rick would know better than I would on that. The cable balance is used to measure mass because they can basically pump in charge to help keep it balanced there. So the more mass you put there, it will require more charge. And then I believe, what is it? I think they're using Ohm's law to help go through it because I equals V divided by R. So I is current equals voltage divided by resistance. I'm not an electrical engineer. I just happen to remember that there. Uh, oh, I actually just 10 to the minus 10 meters. It just happens to be useful. Is there something more there? That would be interesting. Here we go.
See principle to the class of observer rather than the class of universe. This idea is sometimes called the self-sampling assumption, which is that all other things being equal, an observer should reason as if they are randomly selected from the set of all actually existent observers, past, present, and future, in their reference class. For example, we might expect that we, humanity, are a fairly typical example of all the species across the multiverse that can produce scientists capable of anthropic reasoning.
Oh, our human bias is showing. Our human bias is showing. Uh, who says it's? I don't know. I don't know. Here's one of the questions that I had asked Stephen Wolfram for a while. I'm like, are stars alive? He kind of neglected to answer. And then at one point, he kind of commented on it. He's like, it's kind of like if you're talking about like if what do you mean by like alive and stuff? So if you're like, okay, well, something is born. Well, stars born, planets are born. Like, all right, do they achieve homeostasis? Oh, the Earth seems to reflect and give off, and the sun's giving off energy, so it doesn't usually explode. Uh, it achieves homeostasis. Okay, and then does it have an end? Does it die? Does it pass away? Um, stars can go boom. Seems to be an end. Planets can get eaten, torn apart, smashed by things. I don't know. All I know is you go out in the mountains and stuff, you go through some forests, like, yeah, this land is alive. Now there might be things living on it, but I don't know. It seems that the deeper we drill into Mother Earth, I don't know, are we drilling into a silica-based life form? I learned that one from Rick. Thank you. Almost there.
Some universes may produce many more such species than others, and so we
Oh,
might
sorry. So Diodon, that's very interesting. Um, that might explain a lot. It's I'm gonna answer with not now. Stay tuned. We'll see what happens.
expect to find ourselves in one of those. We could also argue that this would be in a universe that has more and bigger galaxies. And more and bigger galaxies will form when dark energy is weaker. In fact, if scientists producing civilizations are rare enough, you might need a universe with lots of bigger galaxies to even have a chance of producing some. All of this pushes the anthropic preference to smaller values of the cosmological constant.
Okay, so basically, the general gist, to my knowledge, is if you get smaller cosmological constant, less stuff is going to be getting pushed around, so to speak. You're going to have the ability for more stuff and things to come together, form bigger, larger galaxies, and thus increase chances for life. I think that's the general anthropocentric argument. Uh, recursion? Recursion is basically just turtles all the way down. It's at least that's the concept. It's basically you're going to keep on going through again and again and again. That's why technically, like if we lived inside a black hole, I think Professor Lee Smolin had conjectured this. It's like, well, what is universe, so to speak, optimized for? What if it was to make baby universes, and every black hole was a universe, so to speak? Um, so that would be a potential way. And then if in each of those you can create more universes, again, it's kind of like the whole. It's like, no, 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 you don't understand. The it's all on the top of a giant turtle or something like that. Or hold on.
World is exists on the top of a giant turtle.
Yeah, I
You
mean,
know, turtles all the way down.
oh my God, I just I just look at some of the deep lore, and I am a troll. Still am a troll, but the sheer fact that I went from trolling Stephen Wolfram just to have some yucks. He converted me into a Wolfram summer school student because I was doing some trolling. He actually gave me some deep answers, and I'm like, I wasn't expecting that. So yeah, yeah, it's yeah. Don't that just beat all? Continue.
To really know whether anthropic selection is the reason behind our small cosmological constant, or indeed any of the other apparently finely tuned parameters of our universe, we need a much better understanding of all the contingencies behind the development of life. But it's still remarkable that Weinberg was able to guesstimate the strength of vacuum energy to within a relatively small range, only based on anthropic arguments.
Okay, so that's the okay. I missed this the first time where I was listening through it and stuff. I just kept going back to the beginning. Uh, so I guess the whole powerful part about all this was that this was before we had any of the measurements from like the 90s or anything. So it's like I think it was Colby, the Planck satellite. So those were I think Colby was maybe like the 90s or something like that, the Cosmic Microwave Background Explorer. So if he did this in the 80s before we actually really had any measurements, that's pretty dang good. I guess that's why it's one of those really, really smart people. Uh versus commenting, maybe you become the Planck constant. Maybe we are. Bill Manuel from Gravity for the Masses channel. He showed me some calculation. You're looking at it, and it's long story short, it's right about at the surface of the Earth, right around sea level. Apparently, um, the calculation shows that you have to almost. Long story short, it's about the magnitude of h bar in slightly different units. Like it's literally like 10 to the minus 34 something, or like maybe joules of energy uh, at the surface of the Earth. And I'm like, he showed me this, and I'm like, what? Why is like the surface of the Earth like at the magnitude of H bar? Like the calculation is like almost exactly at sea level. I'm like, no, no. Now again, maybe that's just a coincidence, but if it wasn't a coincidence, that would be interesting. So maybe we are all Planck constant or something.
And this is the real kicker. When Weinberg made this calculation, we didn't know that dark energy even existed. The accelerating expansion was discovered in the late 90s, a decade after Weinberg's paper. Back then, most people thought that the cosmological constant was almost certainly zero, indicating a perfect cancellation by unknown symmetries. The fact that Weinberg even came within the ballpark of the right number before that number was known is seen by some as a powerful argument for the anthropic selection.
Okay, okay. So again, it's being closer than I don't know, 120 magnitudes off. And again, we seem to get pretty dang close to it without having any actual measurement stuff. Because it's like, yeah, it's a lot of this stuff that I do. That's just Monday morning quarterbacking. It's like I'm just retrodicting, trying to mash data. So it's like if we get new information in and the prediction seems to pan out, that would probably increase your credence, as Professor Sean Carroll might say. So as your credence goes up, like if you just have a random calculation, that's the initial response is it's crazy. There's no way that could be the case. And then you start looking at, and you would talk to some other people, and you look at some more stuff, and it's like, all right. And as you go through, it's like, well, this, it's like, well, no, it doesn't violate this. Okay, it seems to be within the realm of potential possible things. It's like, all right, I can kind of jive with that, but it's like, is is that is that true, or is it like ultimately as you review things, especially if you get good quality experiments, good quality measurements, and if whatever you have seems to hold water, that's going to increase your credence, and the more water your theory holds, so to speak. Let's just say that might explain a lot. We continue.
And let me be clear, the anthropic argument only works if there's a very large multiverse, which is why some might take this as a point in favor of the multiverse hypothesis. Because if all universes are possible, then we need a lot of them to explain our not too rapidly expanding space-time. Thank you to AnyDesk.
Okay, there we go. Oh, we finished it. Oh God, I didn't want to go that last 2.5 minutes. Oh, it's a good thing they're doing commercials. I mute my mic before I cough, and I'm like, I apologize. I'm such a savage. Uh, well, ultimately, here's the thing. It's as a troll, I had asked a whole bunch of folks on Twitter, to which I got no response, which was totally fine because it's a crazy thing. It's like, can we falsify turtles all the way down? The reason why I say that is like, yes, it's a joke, but number one, as a joke, it's like, all right, well, what happens if we were to live into a black hole, so to speak? Oh, let's get even crazy. What happens if we were to live in, I don't know, a neutron, a proton, an electron, or something like that? If we did, and we falsify that wherever we live isn't part of a larger turtle, think Men in Black. The end of the original Men in Black, excellent movie. Um, the end of Men in Black, the galaxy. There's kind of like just a giant alien playing marbles and stuff with the galaxy. So it's like it's kind of that sentiment. And again, it was kind of a joke, but even some physicists have done some black hole coordinate systems where it's literally tortoise coordinates, and here's like a picture of a turtle for the symbology. But that's interesting. Shoot interview. Yeah, Rick. No, you're welcome to come on if you're feeling better. It's again, I want you to focus on your recovery. Uh, yeah. No, if you're ready, we could talk about some stuff. Maybe what was that? Limited calculus. I like that. It's uh I honestly have no idea. I actually have never asked Rick because there actually is the wheel of the win equation. It's like one of the most famous equations. Um, I don't think so. Maybe who knows? It's that would be interesting. So that's all I really got. And then I think a lot of this I might just clip out and do some other things. And oh God, feel bad. How about this? Since let me see if Fizz is on Twitch. So bad. Or Fizz. Be on? I don't see any Fizzy. No, I can't send you over to Twitch. That's too bad. Oh well. So that's all I really got right now. Bubbles and donuts. I mean, who don't like bubble baths and donuts? So, oh, no worries, man. Dude, see, this is why I actually enjoy YouTube, just because, like, I can just go back and watch. Like, I felt bad because I missed a couple of my friends at the Wolfram Summer School's live things. I just went back and just watched, like, the 2 hour thing and just keep it on the background, listen. Uh, but see, this is the way of like people want TV to be. It's like you can actually have like interaction. You can actually like do some things here and then be able to watch it later. That was the thing that always bothered me when they brought those TV things with the interactive guides. I'm like, it says the thing. Why can't I just click on it? Broadcasting, yada yada technology, but now we got the internet. And now, since folks are totally cutting the cable, so to speak. Now you just have to sign up for all those individual streaming packages, and we're back to cable to begin with. Things tend to come full circle. That's all I got for right now. So, hey, thank you all for coming. Peace out. Take care of yourselves. It's a wacky and wild world out there, but yeah, it's open for some new and exciting things in the future. Peace out, everybody.